This week, we will cover the concepts of estimating parameters for populations from samples, how to calculate the required sample size for a desired level of confidence, and conducting statistical inference with hypothesis testing. Let's start with a quick review of how to collect a sample through simple random sampling, known as SRS. To perform this type of study, we need to first identify the population for which we want to analyze. For example, we may want the population of the United States. Next, we need to select subjects by chance, and each subject must have the same chance of being chosen. From the population, we collect our sample to observe variables of interest. In our coverage of the topic, we are interested in either means or proportions. Means are appropriate for interval and ratio types of data, like weights, distance, and age. Proportions are appropriate for nominal and ordinal data that are binary counts, like gender, yes-no questions, and disease status. There is a key concept we will be using in doing parameter estimation. Say you take multiple samples from any shape distribution, and then you calculate sample proportions or means. Then all those multiple sample parameters, such as the mean, will fit as if they came from a normal distribution. Now you can take the mean of all the sample means. This mean of means is sometimes referred to as a grand mean and is written as an X double bar. The same idea holds for proportions as well. We will use this concept as we do parameter estimations. Let's take a look at the measures we will be discussing in this presentation. The first item of interest is called point estimates, which are single values calculated from the data that are meant to be representative. Proportions are written as p hat and are determined by counting all the occurrences of interest x and dividing by the number of all observations. X is the count of all items of interest, like the number of smokers or females in the sample. Means are written as x bar and are determined by summing all the values for the variable of interest, x, and then dividing by the number of all observations. If the x's were the ages of 20 second grade children, then the sum of all their ages would be divided by 20. The next measure is the standard error. It is very similar to the standard deviation of the entire sample, but is for the point estimate. Think of it as the standard deviation of either the proportion or mean. As a matter of fact, the standard error for the mean is calculated by using the sample's standard deviation. Notice the subscripts both for the standard error of the mean and the standard error of the proportion. Also notice that the square root sign is used in both calculations because we are using the variance to get our answer. Next is the error rate, which is simply referred to as alpha. We get to set alpha between 0 and 1, and it is the probability of being in the tails of a normal distribution. For now, just think of it as being the probability of being incorrect. It is used for both proportions and means. Related to the error rate is the confidence level. It is 1 minus the alpha. Since alpha is the error rate, the confidence level is how certain you are in being correct. It, too, is the same for both proportions and means. Since we typically set the alpha to 0.05, the confidence level is usually 0.95, or 95%, and refers to the center portion of the normal distribution. The final measure is called the margin of error. It allows us to put a range on our point estimates, called the confidence interval. Once calculated, we will be certain, by the amount of the confidence level, that the true point estimate will be within the limits of the confidence interval. Notice that the z-score is determined by 1/2 the alpha level, since the error is split between the tails of the distribution. Okay, let's put all these measures together. As usual, the sample parameter, either mean or proportion, is in the center of the curve, which is considered a normal distribution. Each tail represents 1/2 of the error rate, which is alpha divided by 2. The z-score associated with each tail is written as a z with a subscript of alpha over 2. Each half of the center portion of the curve is the margin of error, so the confidence interval is 2 times the margin of error. How do we find these z-scores? Well, first recall that we usually set alpha to 0.05, so the area in the left tail is 0.025. You could use a z-score table or the Excel template for normal distributions. Plugging in 0.025 for a probability yields a rounded z-score of negative 1.96. Due to the symmetrical nature of the normal, the positive z-score is positive 1.96. Alternatively, you could have found the right tail z-score by using a probability of 97.5%, as that is the amount of the curve to the left of the right z-score. Also, recall that the margin of errors use the standard error and not just the standard deviation for all the data. Perhaps the best way to remember this is to view the mean curve in its relationship to the curve of all the data or sample. So, here's what the normal curve for all the data would look like. Now, let's place the distribution of the mean on this curve. Notice that the mean distribution is a small subset of the entire distribution of the sample.